So today, it gives me a great pleasure to talk to so many wonderful friends and colleagues in the robotics community about the future of intelligent machines. And before I begin, I'd like us to reflect a little bit on human activity. For millions of years, humans have been moving and building things, communicating with each other, and thinking. So we have created transportation technology to help us move farther and faster than our biological limits, manufacturing technology to help us build things with precision and scale and accuracy that was not possible before. We built information technology to help us communicate anywhere with anyone in the world, anytime. And then, of course, what we're all living through, artificial intelligence, machines that actually help us think. If you put all these things together, you get a connected, automated driving, self-driving car. So I think it's a really exciting time to be working in this area in robotics. And at the heart, it's really the computer being the most complex machine that humans have ever created. In fact, you can't make today's computer without a computer. But it's more than just a single computer, it's an entire data center. We now have networked computers with vast amounts of compute and storage that change the limits of what's possible. Next. And of course, the robot, when you attach this computer to a physical system with motors, and suddenly you can change the world around you. And it comes down to modeling physical systems. And so if you think about the intersection between physics and dynamics, geometry, and then building models of those things with graphics and computer vision to build perception systems for robots that can reason about their actions. And that's something that I really got interested in when I was a student. And it really comes down to how do we get robots out of the factory into unstructured environments? And I think it comes down to having, got a new clicker now. When you have unstructured environments with unknown obstacles and unknown objects, then suddenly you can't rely on a priori models. You have to do online perception. And then if you've got online perception, then you now have to compute your motion online. You can't use just pre-computed trajectories. And then, of course, you can't rely on predefined sequences because many of those pre-computed trajectories may interfere with each other. So I worked for many years on robot motion planning, and I wanted to tell you a little bit about some of the challenges back then and what's possible today, and reflect on that. Some of the challenges, of course, are that you've got a high dimensional search space. And of course, you have uncertainty in the real world, making your prior models uncertain, and you have a lot of uncertainty in perception and control, and then putting those together in a control loop means that you've got a system that's very difficult to program. Of course, add to that the dynamics and the physics and hard real-time constraints for a system to keep it safe. And one of the things we can take advantage, of course, is computers. And computers are really good at processing data and doing billions of arithmetic calculations per second. And Moore's law has been helping us. So there was a joke when I was a student working on motion planning that I could publish a paper and then just wait about 10 years and then republish it as real time. But if you think about it, reasoning about the consequences of actions, meaning you have a state equation, x dot equals fx u, that allows you to use a forward simulator. And this is key. That means that you can explore the space of actions and then analyze them. And these forward simulators, by the way, can be analytical or numerical. And I'll talk more about that in a later. But one of the important things is how do you actually guide the search instead of doing an exhaustive search, building heuristics that give you more promising actions. And then, of course, one of the great things is that you can actually pre-compute previous plans and store them and use those to make your heuristics even better. So if you start with the classical path planning with optimal search like Bellman and Dijkstra and A*, you can use it very effectively for low-dimensional problems such as navigation. modeling things as a graph. But then when you get into continuous spaces for robots of high dimensions like arms and humanoids, it becomes much more challenging. And I was very lucky in my career to meet Steve Laval. So about 20 years ago, we collaborated on a path planning algorithm that was called Rapidly Exploring Random Trees. And it had some really nice features, very few parameters, very easy to implement. It's biased to explore the large Voronoi regions of the space and converges towards a uniform covering of non-convex spaces. And it's very adaptable to non-holonomic constraints. So just briefly, the RT Connect algorithm was, how do you build a planner out of it? You start growing these trees from the start and the goal, and then one tree is grown towards a sampling distribution, like a random sampler, and then a new node becomes the target for the other tree. So you're biasing the trees to try to aggressively connect to each other. So computing the nearest neighbor, and then adding collision-free branches, and if you're successful, you have returned a path. And then you can, of course, smooth it, and it's been used to solve lots of different problems in the past 20 years in robotics, and many, many different variants of this algorithm have been used. But I think some of the reasons why it was successful was that it was striking a trade-off between optimality and practicality, getting something done that's just good enough, that's usable. So we worked on applying this to manipulation, trying to compute paths for robots. And this, of course, requires IK and trajectory generation. And this was something that we actually presented at IROS in 2000, a long time ago. But this conference was one of the simulators that I had built called the Robotics Automation Virtual Environment, which is now open source as OpenRave and completely rewritten by my student Rosen Diankov, who started Mujin. But the idea was that you were able to actually, even back then, 20 years ago, use this in an online way with stereo vision, compute a path, execute that path for a 7-dimensional arm, and then execute a grasp so that the robot could actually pick up objects. We worked on lots of things with automatic regrasping, and of course, footstep planning and navigation. I don't have time to talk a lot about those, but I wanted to reflect on lessons learned at the time, which was, at the time, there are many parameters to a lot of the models that we were trying to use of both the kinematics and dynamics of the robots, which makes them brittle. Moore's law helps you, but there were still problems that were far out of reach in terms of compute and data. And simulators were either too crude or too perfect. You've heard the phrase, simulation is doomed to succeed. I think the reality is that the gap between simulation and the real world still remains challenging, but getting much better. And I think leveraging what computers are good at is something that all computer science and robotics algorithms are aimed at and trying to optimize for. So I worked on self-driving cars in the early days, built some of the motion planning there. Of course, you've seen what they've done amazingly just previously on how to improve that, and did a lot of other work. But I think the thing that changed at that time was that now suddenly data centers became available. You could actually use them on demand and pay for what you use in terms of data and storage, and I believe that opened up so many possibilities. Also, wireless networking allowed for cloud-connected robots and vehicles to become smarter by crowdsourcing and leveraging data from connected fleets. And this fleet learning and intelligence, or cloud robotics, we used to really parallelize the grasp selection, which is a big problem in manipulation planning. When you're trying to pick up an object or even an unknown object, how do you decide which grasp is good? So this was one of the first early works on cloud robotics I did with my colleagues at UC Berkeley, trying to build robust grasping. But machine learning really was the key: neural networks, deep learning, transforming vehicle perception. And I think that was a huge advance. A lot of the brittle models that were used before just couldn't compete with the neural networks, and that was really exciting. And at the same time, automobile industry was transforming with the so-called case, all these factors that were disrupting the industry. So I made a jump to join Toyota, which was transforming itself to a mobility company. And this is something that involves both automotive technology as well as robotics technology. And one of the things that we were tasked to do was to try to deliver new kinds of autonomy and safety with Toyota quality and reliability. So we worked hard to deliver to the market last year our advanced drive product, which is available now on the fuel cell second generation Mirai, as well as the Lexus LS500 on, it's called Lexus Advanced Drive. And this has ramp-to-ramp automated driving hands-off in highways. Now, it was also the first example of deep learning in production at Toyota and Lexus, which our company is quite proud of. But we had to do a lot to really make that happen. And I wanted to reflect a little bit on how that happened. So deep learning, of course, has been revolutionized with computer vision, perception, prediction, and planning, the three hard P's of robotics. And in this work, we're trying to simultaneously estimate pose, both 2D, 3D, scale, and shape at the same time using modern machine learning. And one of the things that you realize when you start working on this, especially with domain transfer and sim to real, is that analytical and statistical models actually can complement each other. Meaning that I've heard a lot of people say that they just want to replace all of the models with an end-to-end system, just map sensor raw inputs to actuation. I think that won't work for a number of reasons. First of all, we need to make systems that are explainable for safety. But there are other reasons why I think it's kind of a false choice to use one or the other. We can actually use both. The graphics is getting so good now that we can do and use domain transfer and sim to real and generative adversarial networks to create really photorealistic simulations and then test them all in the cloud, meaning that you can test a very long tail of high risk but low probability events and try to find and increase the probability virtually of dangerous things happening. These are things that you wouldn't really stumble upon in the real world unless you had millions and millions and millions of miles, which is impractical for actual testing. So it really comes down to model-based design and machine learning. We can use our knowledge of physics, our knowledge of vehicle dynamics and control and safety envelopes and Lyapunov functions and combine them with machine learning, things that allow us to statistically estimate the gaps of the model. And I believe they really complement each other in terms of filling in the places where we have unknown parameters that are hard to estimate in the models. And that's something we can use data to do. So when we think about machine learning, optimizing parameters for candidate trajectories, learn from traffic data or human driving examples actually provides a scalable way for us to build systems that can navigate smoothly and behave normally in human traffic. And actual vehicle control executed with functional safety, bounded by safety envelopes. And I think this is a really important thing, being able to have good explainability and quality assurance at the same time that you're building systems that are taking advantage of the cutting edge in neural networks and machine learning. So this is some work that is actually published here at IROS today for some of my colleagues. I won't explain it. You can see it in the conference or go to our booth, but it's really leveling up that early work in evaluating grasp candidates with simulations. A robot being able to simulate millions of different possibilities before deciding which one is the best is really a great way to really think about the consequences of actions at scale, which was really not possible 20 years ago. And if you even think about DeepMind, probably the most famous recent example of AlphaGo and AlphaZero, many people focus on the neural network, but actually there's a Monte Carlo tree search at the heart of it. right? It's logic and planning and reasoning, but the neural network is learning the heuristic and guiding the search, right? It's a perfect combination. So here's the question. When we think about artificial intelligence, we think about intelligence and cleverness and logic. So if you need to go somewhere in downtown Manhattan, you could choose someone who is a genius, a chess champion who has, super high IQ, or you could someone who didn't finish high school but has driven 30 years in Manhattan without an accident. It highlights the difference between intelligence and experience. And so sometimes we talk about machine learning as AI, but I actually like to think of it as AE, meaning it provides experience to the system. So intelligence, logic, and reasoning versus data. And in some sense, artificial intelligence is a kind of wisdom. Artificial experience is a kind of wisdom. So in order to bring this all together, to make a good robot, you can't just have good software. You also need good hardware. And you actually need both to make a great product. And that's really hard. And so that's what Woven Planet is about. We started this company to try to bring the best in terms of quality software and quality hardware together. And you can come see our booth. But the key strategy is many people focus on delivering automated driving by focusing on the onboard software, just making the best onboard software. But it turns out that in order to make the onboard software defect-free, you have to actually have a whole bunch of other software, whether it's machine learning training, all of your developer tools and CIT, your simulation for sills and hills, deployment tools and mapping and data management. And together, 90% of the total software that you build is actually off-board. And the reason you need that software is because you want to make the onboard software high quality and reliable and defect-free. So what we're trying to do is actually do the Toyota Production System, or TPS, for software. Toyota Production System is renowned for making quality hardware at scale that's affordable with high quality and durability and repeatability. And that's what we're trying to do for software. And when we do it, we have to think about what is our goal. Many times, as a technology enthusiast, I forget that the goal is not the technology itself. It should always be to help people. How can we create technology that helps people? And when we think about the cities of our world, right now, we live in urban environments that are becoming even more populated as the world concentrates its population in urban centers. And growing fast. Mobility needs are growing. And all these cities are faced with the problems of traffic and pollution and sustainability. And when you look at the traffic that's all mixed together, one of the things we're exploring at Toyota is a new concept called Woven City, which is trying to build a grid of mobility lanes where you have vehicle traffic, intermediate mobility, and pedestrians with different places to move, and it's woven together into this grid. And this is actually on the former site of the TMEJ factory at the base of Mount Fuji, not very far from here. And this is now under construction. This started during the pandemic, but the earthwork is done for phase 1. And now we're busy actually building this city as a test course for new mobility and robotics. So it should be open within about 2 years, but we're really excited at trying to accelerate robotics and AI and mobility technology at this site, which is at the base of Mount Fuji. And its test track as a mobility innovation is really different and distinguishing from many other smart city type of projects. And it's really meant to be about how we create technology to help people as a living laboratory that's ever evolving and never finished. And trying to test these in real world, real life application settings. Of course, we're going to leverage as much as possible digital tools to accelerate, just the same way computer-aided design tools have dramatically improved our ability to design automotive technology. We can now create digital twins, and we can test drive models of cars before they've ever been built, just at the concept stage, using virtual reality and augmented reality. And so we've created a complete digital twin of Woven City that we can use now to test and regression test our applications. For example, if you wanted to ask a question, how many charging stations would you need to support a population of 10,000 people with 5,000 mobility devices? And where would you locate them? That's something you can simulate at scale and test at scale using this digital twin. We're also looking at mobility of goods, people, and information. So the mobility of goods are done by robots. And we have a lot of things that you can see in our booth around these mobility robots, but we can actually test them in the digital twin. What would it take if a delivery robot, how can we optimize it so that the maximum latency of delivery door to door is less than 10 minutes, something like that. And of course, we've been collaborating with our colleagues at Toyota Research Institute to really think about how we can build robots in unstructured environments that can help support people's aging in place and help people with tasks that otherwise they may not be able to accomplish by themselves. And this is something that's very hard. I think there's still a lot of work to do, but I'm really excited about combining these models of the physics and dynamics with statistics and machine learning and lots of big data. So I think I don't have time to go through all of the robots that you can see. We're developing some different prototypes, dual arm with perception, and really modeling both the dynamics and kinematics, but as well as learning the hard parts of the models using machine learning. So you can see those, some of those more in our booth. I'm just going to skip. This is an interesting robot morphology that tries to free up the floor space by using a gantry overhead. And of course, we have a complete digital twin of this that allows us to do automated testing and regression testing at scale. So when we think about artificial intelligence, many times people think about AI as replacing us and in some sense almost dehumanizing us. But in the literature, before AI became popular, there was actually another branch of thinking called IA, which is intelligence amplification. And I kind of like this because it really clearly puts the human at the center. We're building tools to help people and amplify our abilities. And so I think that is the key message, is can we create robots and technology that helps amplify human potential instead of replacing us? So here's some closing thoughts. First, as I mentioned, I believe that robots should really help support and amplify human abilities, and that data-driven and analytical models are very complementary. There's no need to abandon physics and math. Statistical models can fill in these gaps and create more reliable, high-performance systems that can be explained and analyzed, and the behavior can be bounded. I also really like the combination of logic and data coming together to form intelligence and wisdom. So in some sense, artificial experience creating the complementary skill set of intelligence and reasoning. And safety and quality really mattering. We should design robot systems that have bounded behavior that humans can understand, control, and improve. And this is a big challenge. Let's take advantage of deep learning, but build systems that we can explain and understand, and more importantly, control and analyze and bound. And the ultimate purpose is, of course, to provide health and happiness for people and our planet. And this is something that I think all of us can get behind. So please visit our booth, and thank you very much for your attention.
Thank you, James. I myself very much impressed to hear the spectacular plan of Toyota. Yeah, I think many of you have questions or comment to him. Please come to the microphone. Okay, please.
Hello. Thank you for the great talk. I think many of our aspirations among all of us here sympathize with your vision that data and AI are complementary things. and human logic and AI in that are complementary things. And I think the big question is, how exactly do we bridge this gap, right? And many people thought that, well, okay, symbolic AI might actually get us there because logic is expressed in terms of symbols, but they're still far away from actually being able to express all of our logic in this sort of very black box representations that are learned by data. So I was wondering if you have any thoughts about how exactly this bridge can actually be constructed so that we can achieve this connection between logic-driven AI and data-driven AI.
Yeah. It's a great question, and I think it really does depend on the domain. But I guess my main point is that I sometimes hear people that are really enthusiastic about machine learning abandoning math and physics. And for example, would it make sense to train a neural network to make a GPS receiver? I could learn GPS coordinates from raw RF signals from satellites. But it would be silly to throw out satellite physics and general relativity because you can get so much of the model in a really compact, accurate way. The parts that you can't model well are things that you can model with data and learn with data. So I think most of the problems that you're trying to solve have that flavor. We can get a very compact analytical model, but then fill in the gaps, fill in the hard parts with data and statistical models. I mean, at the end, motion planning is search, and if you open the box of a neural network, it's doing optimization, which is also search. And you're basically trying to, find a fitness function, and of course, that fitness function may also have models in it. So to me, I think there's really great potential to not like throw the baby out with the bathwater. Like let's continue to learn physics and dynamics, but at the same time leverage big data and use neural networks as a way of having really good function approximation.
Thank you.
Okay, thank you very much. That's your yes, please.
Thank you for your presentation. I'm a student of Toyota Technological Institute. You will be small. Yeah, I only have a simple question. You mentioned the cloud-based analysis for self-driving car. If my understanding is correct, it takes much time to communicate the cloud system. So do you consider the current communication speed is enough for self-driving car?
You mean communication speed of data within the system?
Yeah.
I think there's obviously more is better. And if you think about, what has transformed robotics, wireless technology has improved so much in the past 20 years compared to Moore's law. Almost 1,600 times more speed and bandwidth is capable now wirelessly. But when we think inside the car, if we've got wired technology, absolutely, I think, being able to transfer data among each of the different components. And I think the architectures are moving towards central ECUs. So central ECUs with shared memory and very good functional safety and redundancy. I think that could be allow us to have a lot more capability in the future. But I would still say it's an open problem, and I'd say there's still room to be improved, for sure.
Yeah, thank you.
Okay, thank you very much. I'm sorry, for the sake of time, I have to finish the questions. Okay, I'm PC chair, so I need to keep in time. Sorry. Okay, James, thank you very much, and please give your big hand
so
to
much.
him.
Thank you.
Thank you very much.